All right, so if you've ever played around with electronics, you've probably used Ohm's law for just about everything. And yeah, it's a fantastic tool. It's like the trusty hammer in your toolkit. But what happens when circuits get really tangled and complex? Well, a single hammer just isn't going to cut it. You need a whole toolbox. And today, we're going to build that toolbox piece by piece so you can look at any circuit and know exactly how to tackle it.
Just take a look at this thing. It's a classic resistor bridge. And at first glance, you might think, okay, resistors, no big deal. But then you look closer and you realize, wait a minute, none of these are in a simple series or parallel configuration. It's a puzzle. So how in the world do you solve it? How do you figure out what's going on inside this little maze? That's the exact challenge we're here to solve today.
So here's our game plan. This is a look at the tools we're about to add to our collection. We're going to start with the absolute bedrock, the fundamental laws that govern everything. Then we'll get into the real power tools, mesh and nodal analysis. We'll even cover the special attachments you need for those really tricky situations, and some clever shortcuts that'll make your life way easier. And finally, we'll cover the most important skill of all, knowing which tool to grab for the job at hand.
Okay, first things first, let's lay the foundation with Kirchhoff's laws. And let me be clear, these aren't just helpful tips or guidelines. These are the fundamental, unbreakable laws of the circuit universe. Think of them like gravity. Every other tool, every other technique we talk about today is built right on top of these two rules.
First up is Kirchhoff's current law, or KCL. And honestly, it's about as intuitive as it gets. Imagine a pipe with water flowing in that then splits into 3 smaller pipes. The amount of water coming out of those 3 smaller pipes has to equal the amount of water that went in, right? It's the exact same principle for electric current at a junction, or what we call a node. Simply put, what goes in must come out. You can't just create or destroy charge out of thin air.
And the other side of the coin is Kirchhoff's voltage law, KVL. If KCL is about the conservation of charge, KVL is all about the conservation of energy. Here's an analogy. Think about walking up a hill and then back down to where you started. The energy you gained going up is exactly equal to the energy you lost coming down. You end up at the same elevation. For any closed loop in a circuit, it's the same deal. The sum of all the voltage gains from sources and the voltage drops across components has to equal 0.
And here are both laws in action, side by side. Over on the left, you see KCL. You've got this one current, I1, hitting a node and splitting into 3 paths. KCL just tells us, plain and simple, that if you add up I2, I3, and I4, you're going to get I1. Now look to the right. That's KVL. We trace a path around that single closed loop. The 20-volt push from the battery is perfectly balanced out by the voltage drops across those 2 resistors. It all adds up to 0. See? Perfect balance.
All right, with those fundamental laws locked in, it's time to pull out the power tools. I'm talking about mesh and nodal analysis. These are your heavy-duty, systematic methods for taking a circuit that looks like a total mess and breaking it down into a simple set of equations that you can actually solve.
So what's the difference between these two? Well, it really just comes down to what you're looking for. There are 2 different ways of looking at the same problem. Mesh analysis focuses on loops. It uses KVL, the voltage law, to figure out the unknown currents flowing around those loops. Nodal analysis, on the other hand, focuses on the nodes. It uses KCL, the current law, to figure out the unknown voltages at those nodes. Different approaches, same goal: to completely solve the circuit.
Let's break down mesh analysis. It's really just a simple 4-step recipe. Step 1, you identify all the window panes, or independent loops in your circuit. Step 2, you just draw a little circular arrow in each loop and give it a name, like I1 or I2. That's your mesh current. Step 3, you apply KVL, the voltage law, around each one of those loops to get an equation. And finally, step 4, you take those equations you just made and solve them. That's it. It's a method that just works.
And here's what that looks like in the real world. We've got 2 clear meshes here, right? So we define 2 currents, I1 and I2. Then we just go around each loop applying KVL. That gives us 2 equations for our 2 unknown currents. And once you have 2 equations and 2 unknowns, well, that's just algebra. We can solve that and find the exact value of both currents.
Okay, let's flip the script and look at nodal analysis. The process is going to feel really similar, but instead of loops and currents, now we're thinking about nodes and voltages. So step 1. Find all your major connection points, your nodes, and pick one to be your reference point, your ground, or 0 volts. Step 2, give all the other nodes a name, like VA or VB. Step 3, apply KCL, the current law, at each of those nodes. And step 4, you guessed it, solve the system of equations you just created to find all the node voltages.
Let's take a look at a nodal analysis example. In this circuit, we've picked out 3 main nodes, A, B, and C. So we'd apply KCL at each of those points to build the equations we need. Now, you might be looking at that big dotted circle around all 3 nodes and wondering, what's up with that? Well, that's actually a little sneak peek at a special trick for handling tricky situations called a supernode, and we're getting to that right now.
So you're chugging along, doing your mesh or nodal analysis, and suddenly you hit a wall. There's some weird component right where you don't want it. What do? Well, for these special cases, we have a couple of special attachments for our power tools, the Supermesh and the Supernode.
So let's picture this scenario. You're using mesh analysis, which relies on KVL, the voltage law. But then, bam! There's a current source sitting on the line between 2 of your loops. That's a problem. How can you write a voltage equation for a loop when you have no idea what the voltage across that current source is? It seems like you're stuck.
But the solution is actually pretty brilliant. It's called a supermesh. You can see it here in the diagram. We basically pretend that pesky current source in the middle doesn't exist for a moment, and we just trace one big KVL loop all the way around the outside of both meshes. That gives us one of our equations. Then, we get our second equation by looking at how the 2 mesh currents, I1 and I2, relate to that 6-amp source they share. And just like that, problem solved.
And you know what? This exact same idea works for nodal analysis too. If you ever have a voltage source stuck between 2 of your main nodes, you just group them together and treat them as one giant supernode. It lets you apply KCL to the whole group at once. It's the same clever workaround, just for a different problem.
You know, sometimes the smartest move you can make is to simplify the problem before you even start solving it. This isn't about using a fancier tool, it's about making the job easier in the first place. It's all about working smarter, not harder.
And the most direct way to simplify is just by combining resistors. Look at this example. You can see this complex-looking network, and step by step, we just chip away at it. We find 2 resistors that are in series, combine them. Find 2 that are in parallel, combine them. You just repeat that process over and over, and suddenly, this intimidating mess gets boiled down to something you can solve in your head.
But what happens when you can't simplify anymore? What if you have a circuit like our original bridge puzzle? Well, that's when we bring out the heavy artillery, Thevenin's and Norton's theorems. And these 2 are absolute game changers. What they say is that any messy, complicated linear circuit, no matter how many components it has, can be boiled down to something incredibly simple, either a single voltage source with 1 resistor or a single current source with 1 resistor. It's kind of like magic.
I mean, just look at this. That whole circuit at the top, with all its sources and resistors, is completely electrically identical to that simple little thing in the bottom right corner. A single current source next to a single resistor. That is the Norton equivalent. This is so powerful, especially when you only care about what's happening at those 2 points A and B. You can just replace the entire rest of the circuit with its simple equivalent.
So, we have loaded up our toolbox. We've got fundamental laws, power tools, special attachments, and simplification tricks. But having great tools is only half the battle. The true mark of an expert is knowing which tool to pull out for which job. Strategy is everything.
So think of this as your quick reference guide. Before you start any problem, just take a second to look it over. Does it have fewer loops than nodes and a lot of voltage sources? Mesh analysis is probably your fastest route. Does it have more current sources or fewer nodes than loops? Go with nodal analysis. It'll be less work. Do you only care about what's happening at one small part of a huge circuit? Don't solve the whole thing. Use Thevenin or Norton. And of course, your first question should always be, can I simplify this thing first?
And that really gets to the core of great engineering. You know, anyone can eventually solve a problem if they just throw enough time and brute force at it. The real skill, the art, is in finding the cleanest, the most efficient, the most elegant way to get to the answer. It's about seeing the whole toolbox and instinctively knowing which tool is going to make the job easy.
Which brings us full circle, right back to our original puzzle, the resistor bridge. I want you to look at it again, but this time it's different, because now you're armed. You have a full toolbox. You know Kirchhoff's laws, you've got mesh and nodal analysis, you know about super cases and equivalents. So what's your first move? Which tool do you reach for? The answer to that question is what really matters.